Welcome to the first of the series on differential equations. So we're going to take a switch to the the pure content of the course now. But hopefully, like we said in the series on the exponential distribution in the stats side, you saw that the pure mathematics was the basis really for, in that case, for the applied mathematics, which is the name given for statistics, and it literally applies the pure mathematics to the real world. So differential equations is naturally all to do with differentials, which you've had lots of exposure to in the past, just perhaps in abstract context, just working with dy by dx, you're working with differentials. And then more so this year in year 13, you'll then be applying this into a context. Because the idea of derivatives is very much analogous with nature. This is kind of how in the real world the mathematics models situations, because dy by dx, or perhaps more commonly we're going to be using, let's say, dy by dt, where t is time, is going to model some kind of rate of change. So be it population growth, be it some kind of money-related interest growth rate, decline rate, whether it's the most current thing at the moment in terms of a virus. No doubt if you were to search for differential equations and coronavirus, there will be absolutely tons of stuff out there, and it'll probably get quite complicated. This is a huge field that branches way out into physics and the rest of science, so perhaps not the kind of thing you wanted to sort of dive into straight away, but that's kind of a bit of the reason behind it. Before we make a start, I think it's worth reminding people the kind of the second part of the title. So we're calling the topic differential equations. We've just spoken a bit about differential, but equations, it's kind of easy to get wrapped up in this topic and forget that you are just dealing with equations, and with equations we usually want to solve them for a particular purpose, of course. And I guess I just want to start by asking you to cast your mind back really to when you were first encountering equations, so back in primary school, start of secondary school, and how you've developed really over time since then. So you'll build your skills up, and you get to a stage where you've got no difficulty solving something like this, for example. Oops, that's not. Let me just see if I can get this to focus. Not the best. One moment. That's a little better. But over time, you sort of learn to develop your skills, and you end up being able to do calculate or sort of solve, I should say, much more complicated things, and there might be more things going on. Okay, but usually, you develop, and you come up with approaches to solve these kind of things, and then you kind of, let's say you hit something like this, and maybe I'll change the variable. Let's put it in standard kind of form as well. Why not? And all of a sudden, the techniques that you have known to date don't really work anymore. You try and solve that in the typical way that you would do with a linear equation, and you run into difficulties, and hence you end up searching for new techniques. And you'll be so experienced with these, I'm sure one or two approaches will jump straight out, but there are a number of ways we could go about solving this, and really we're only sort of touching the tip of the iceberg here, because we could look at the cubics, which you perhaps have looked at a little bit in year 12 anyway, but what if you go beyond that? What if we don't just go for nice integer powers? The world's your oyster in terms of this. You could come up with all sorts of awkward and horrible equations, and it's almost a bit kind of disheartening, but also kind of makes you open your eyes and go and realise we really only know how to solve a very small selection of the possible equations that are out there. So a differential equation is just a different type of equation to get used to, and as we said, it's one that involves some kind of differential. So perhaps we have dy by dx, and maybe we have something like this. Perhaps we have it something like this as well. Okay, and essentially it's an equation that involves, like I say, a dy by dx or maybe dy by dt, and not that it has to be y. So quite often what we're going to be searching for when we try to solve something like this, like a differential equation, is that we'll be looking to try and get a solution in terms of y's and x's. Okay, perhaps it'll be y equals, quite commonly, some function of x. And in the long run, because we're going to do this quite abstract initially, but in the long run, when we make this and attach it with context, the y and the x, maybe it's y and t actually, the y might be, let's say, well, something very current would be obviously, the number of infected people, and t might be the time rate. So you could input the t into your function of t, and it would spit out the number of infections. Okay, so this is then the format that you'd want it in, but you may have only originally known some kind of rate. And again, just to keep it current, they're talking about the R rate of infection, and if we can establish that, perhaps we can work away from this kind of form into this kind of form. Okay, so that's sort of often the gist of it, and you might not always be able to get it comfortably as y equals and y is the subject, but perhaps you'll have some kind of y's and x's. But the point is that you've dealt with the equation so that it's no longer a differential equation. Okay. So that's sort of the idea behind this. So if we look at, let's start with a fresh page, and let's start with a title. So we are going to be considering differential equations that are of the first order. So I suppose a non-example is easier here, so we're not going to be looking at the second derivative, d squared y by dx squared. We're just going to be looking at things like dy by dx involved, so it's just a first order. And the only reason I said oops there was that I just wanted to write an ordinary differential equation. But I just missed that out there. So ordinary differential equations, which will be referred to as ODEs for short, and the ordinary is essentially just a nod to the fact that it's going to be the independent variable. I keep on referencing time because that's the most common. Sorry, what I'm trying to say is there's only one of them. Okay, so you can have partial differential equations in which there are several variables, but we're going to be looking at the cases where there's just one. So, as even you get this with we looked at kind of going from sort of your more simple linear equations at the very start to then a jump to a quadratic equations, but even these, which is now kind of perhaps a more basic level in some ways, even these have their own difficulties, as we know, because you may factorise this one perhaps, but then you learn that actually no, they don't always factorise, and so some methods work for some cases but not for others. And so a lot of the skill in this topic is in developing the sense of when can you use one approach, when can you use the other, why does it break down and why does it work and why does it not, that kind of thing. So in order to do this, let's start with some kind of expression. And I think from my notes I've taken the odd example perhaps here from other YouTube videos, but that's not an issue. So here we go. Now this, granted, is not a differential equation. Okay, I'm going to kind of work this the other way around initially. So if we take this, for example, like I say, we're going to do it without a context for pretty much all of this series, really, and that will come later in the course when we apply the context. Let's see what happens when we differentiate with respect to x. So 5x squared, differentiate that with respect to x, we get 10x minus, now we've got y cubed, and what I perhaps should have said at the outset is that it's implicit, it's implied that y is, in this case, y is a function of x. Okay, it's not just acting as a constant. And in fact that leads us to having to do implicit differentiation, which you will have done in the single part of the course. So as a kind of recap of this, if we were hoping to differentiate with respect to x, our y cubed, then hopefully you recall the kind of nice, not trick, but a nice sort of clever step of logic, which is to say, well, if I want to take d by dx of y cubed, with y being a function of x, then dy by dx multiplied by d by dy, hopefully you can see that these two would cancel to leave d by dx, which is what I've got here. So I can just say that actually this is the same as dy by dx times by d by dy of y cubed, and hopefully just with almost a visual representation, and you can see that these are actually the same, they are equivalent. And that's handy because if I consider just doing this bit together, then I can differentiate quite easily y cubed with respect to y, because I get 3y squared, and it's just a bit more common, but it's not necessary to do this bit first. But just doing that bit first, I get 3y squared times by dy by dx. So that's a kind of recap of that bit, which enables us to deal with the y cubed. So if we pop that in, we have a similar issue over here. Okay, so we can kind of apply it in a similar sort of way, and we'll end up with 4 times by dy by dx. And then obviously the plus 4 when we differentiate with respect to x, that will just become 0. Okay. There's a plus x as well. When we differentiate the plus x, we get 1 when we differentiate with respect to x, and then differentiate the 4, we get the 0 I just mentioned. Okay, haven't really explained sort of what we're working towards here, but this is going to be something that you'll be doing in the single maths side of the course if you've not yet done so, which is trying to work from something like this into a differential equation. So trying to find an expression for dy by dx. So the hard work's kind of been done because we've now generated a dy by dx. It's happened to have occurred twice. But a little bit of rearranging gives us the following. And if we also factorise the dy by dx, so factor that out, then a simple division of 4 plus 3y squared on both sides gives us what dy by dx is. Okay, so there's just an example of kind of going the other way round to my introduction, if you like. So we've been given an equation that's not a differential equation, and actually we've turned it into one. Okay, so we've got a differential equation in terms of x and y. However, the focus of this topic is going to be to do it the other way around, like I say. So we're going to be given the differential equation and asked to essentially solve it, in other words, to find it in terms of, in our case, x and y. Okay, so using the same example, we should hopefully get back up to where we started. And here's a very sort of recommended technique, I suppose. I think this is probably what I would try in most circumstances, until you get a sort of an eye in for the different approaches, is if you actually note that we've got some x's or an expression in x on the numerator, an expression in y on the denominator, and a similar kind of thing over here. We can apply a technique called separating the variables, which may be something that you've come across, perhaps in single maths. And if I multiply both sides by 4 plus y squared, and I'm also going to, in the same step, multiply both sides by dx, I get the following. And it just so happens that this is the perfect form for me to integrate, because I have a function that's purely in terms of x dx and a function that's purely in terms of y dy. So if I integrate both sides, the two values will still be equal. Okay, and the key step, like I say, was separating the variables so we don't have this mixture of x and y's together. Now I can go about and do the integration. So we get 4y plus 3y cubed over 3 plus a constant, don't forget, so you might call that a or b. Quite often you'll see it as c1, because you can see that there's going to be another constant arriving shortly. If we integrate this side, we get the following, but you'll also get a constant, so let's call it c2. You may well see that this is sometimes no constants written here, and a constant is just written on the one side, and that's essentially taking account of this one, because I could always subtract c1 from c2 and just call it, you know, any letter really to represent a constant. So I could do that. And so let's see where this leaves us. We're kind of keeping half an eye on, you know, where we started originally. Well, we're kind of there, are we not? So we've got 5x squared upon rearranging minus y cubed equals 4y. Have we got a plus an x? Just wondering why I've got a minus x. 4y plus y cubed. Sorry, that is correct, yeah. 4y plus x, and there's going to be some kind of constant. Let's just call it c3. And so you can see that actually there's a bit of an issue here, and this is a common issue, okay, that you can see quite regularly. Let's just do a quick aside. Because if we had something like, I don't know, let's say we differentiated x squared, which guarantees to give us 2x, okay, so that's fine if we differentiate with respect to x. But the converse, if we integrate 2x with respect to x, what do we get? Well, could be x squared, but as we know, we get a constant. And so actually there's an infinite number of solutions here, because that constant could be anything. No matter what c is, if you differentiate it, you get back to 2x. And that's obviously causes a slight difficulty with the with integration in many cases, because of the constant. We don't necessarily know what that is. So, you know, okay, perhaps if we had some context, we might know that it was 4. In this instance, I don't. So we get what is called the general solution. And it might look a bit funny that a solution, you know, is given in this form, but that is the general solution of the differential equation that we started with up here. And kind of, as you'll see further on in the course, we would need to have some specific information about the situation, assuming we had some context, in order to determine what this is. So we might have this at the start, and then we may also be told that, oh, by the way, it is observed that when y is such and such a value, you know, when y is 8, for example, x is whatever value. Yeah. So if y is 8 when x is 2, for example, then of course you'd be able to substitute these in, and the only thing left to determine would be c3. So you would need a specific piece of information in order to determine what is that actual constant in that particular scenario. Okay, but with no context, that's redundant in this instance. So I kind of wanted to show that and how it links in with the other part that you might do in the course, because it is essentially just the, doing it the other way around. And let's just have a look whilst we're doing that at a more simple case. So here's a sort of a trivial one. So we've got a differential equation, and let's just have a look at something like this, for example. Okay, you will become very familiar with this form, and they don't always have to be in this form, but equations in this kind of form are very often solvable by using the separating variables approach, and upon doing so, a quick bit of rearranging makes it nice and straightforward to get to that step. We can then integrate. I might do what I referred to before and put the constant just on the one side, so even though there would be a plus c there, let's amalgamate the two constants that we would get and just pop one constant on for simplicity. And what else can we do? Well, we could just multiply through by 3, I suppose, just to make it more simple. I can either put 3c or I can put a different letter and just kind of, as long as I'm aware perhaps that a equals 3c. It's kind of dependent on the situation as to whether that's more convenient or less convenient. And there's my general solution once again. Okay, again, I'd need to know what x and y were in this specific case if I were to find out the value of this constant. But we started off with a more tricky one, if you like, just to show where it came from. But actually, here's a kind of simple example. It's not as hard as it looks at first, provided you can, like we say, separate those variables. So I think we'll just do one more in this particular video. Oh, no, we'll do a couple more whilst we're on it. Okay, and then it might be worth searching for some questions on separating variables. So let's have a look at, well, if that was example 2, let's have a look at a third example. So here's the question. Like we said, there's going to be so much technique in terms of all the approaches you've learned in the pure mathematics side of the course, just since starting A-level alone, that we're going to strip back the context initially, so that we can focus on the mathematics, if we like. Okay, so this is marginally different to the form that we set up here, but let's just have a go and see what happens if we attempt to isolate the variables on each side, the x's and the y's. So if we do that, and we can do it in a couple of steps, I suppose. How should we do this? With practice, you can kind of do this very quickly, and depends on your algebraic fluency and skills, I suppose. We can multiply both sides by dx. We'll just do it a couple of steps at a time. Multiply both sides by dx. We could now, let's say, divide both sides by x squared plus 1. So that's got rid of all the x-related terms on the left-hand side. Leaves us with a bit of a mess on the right. But we've still got a y on the right. So if we divide by the y, then we get dy over y. Let's write it as that for now. And then we've got this kind of awkward mess here, x dx divided by x squared plus 1. Okay. This might feel more comfortable if we were to write this as 1 over y multiplied by dy. Just looks a bit more familiar. And similarly, x over x squared plus 1 multiplied by dx, which is of course just the same. That's just basic fraction work. Okay. Of course, looking at this, we must be tempted not to avoid one of the most common misconceptions and simplify this incorrectly. Think that we can divide the x by the x, that kind of thing. And in a similar way up here, we need to be careful that we don't think that we can actually cube root both sides and get y equals x. Okay. So we're at that stage where we've got it in a perfect form to integrate both sides. So let's do so. Okay. And what does that get us? Well, we've got integral of 1 over y dy gets us ln of y, which we should have studied in year 12, plus of course the constant, which I'll amalgamate into the constant that will come out of the right hand side. And then we've got this sort of issue here. Now I don't know whether to do this in this video or the next video. Let's see, where will it fit in more nicely? It is tempting to do it on this stage. No, I'll tell you what, we'll look at a different approach for now, where we say, let's say you're not sure how to do this, or even that one, and we go for a substitution. So let's say you've had a lot of practice of making your own substitutions last year, so let's make the denominator equal to u, which means that du by dx equals 2x, which means that du over 2 equals x dx. So you can see that my u, the denominator I've already got in terms of u, brilliant, and this bit, the x dx, remember you can think of that as x dx, like up here, I've now written as follows. And the more practice you've had with that, the quicker you'll be. Different ways of laying that out, but that's the gist of it. So that's going to be the exact same. Let's just say I'm going to integrate this over here just as an aside. So I've got x dx is du over 2. Let's pull the half out. Okay, and we've got the du, which is going to multiply. Well, all that's left is 1 over the denominator, which is 1 over u. Okay, so upon solving this, we get the following. Okay, so we can write that in, but obviously we can replace the u with the x, so we get a half ln, and u is x squared plus 1, and then I need my constant that's going to take account of both constants and integrations as follows. And there we go. Okay, it's got some sort of nastier ln's involved, but nonetheless we still have a general solution. Once again, we'd need to know a specific value of x and y, like a coordinate almost, if we were then going to go on to figure out what this c value was. Okay. So I might do another one which involves some natural logs. As we'll see, that'll become more involved actually as this goes on. But I might explain in another video sort of the quicker step, and well done if you've already spotted it, as to how to get from this to this straight away. Okay, so let's finish with one final video where it is still possible to separate the variables. So let's say for the fourth example we have a look at x take 4 multiplied by dy by dx, and say that happens to equal 3y. Okay. So we'll attempt to separate the variables, see where that leaves us, and which order should we do this in? Let's see. If we divide through by y, keep the dy on the left, and then multiply by dx but divide by x minus 4, and I'm just going to speed things up here by doing the integral at the same time. Then I didn't really leave enough space to take the constant 3 out, but you should be good enough with your algebra to follow this, so you know, pause the video if need be and just check that you're happy with getting to that stage, and in a kind of nutshell we can sum this up using the ideas from before. Again, I could have taken the 3 out, it's going to just be a constant factor, so we end up with ln of x take 4, and there's my c. Okay, and depending on either the exam question or the form that you want it in, depending on the question, what else could we do? We could write this as, let's see, ln of y equals ln. We could bring the power of the 3 up as a power if we wished. We could even subtract this bit from both sides, and then using our laws of logs, we've got log of a essentially minus log of b. And we could write that if we wanted to. It kind of depends what's most useful in the scenario though. So we get the following, that kind of thing. Let's even go a step further and take the exponential of both sides. Okay. And let's see if we can work it. We're almost there now, to work it all the way to the stage where we get y equals, and so multiply both sides by x minus 4 all cubed, And you might more commonly see this written as some constant, which is what e to the c will be, because remember c is just a constant and e is just a number, don't forget. So we've got a x minus 4, but it might be worth noting where all I've literally done is just replaced e to the c with a. Okay, so there's another way of looking at solving an equation that happens to be a differential equation, and there's only a few kind of steps there that are different to things that you have done in the past. It's just a kind of different way of thinking about things, and it's putting techniques together that you already know. Okay. In the next video, we'll probably take it up a notch and have a look at situations where it's not quite so simple just to do this, because at the minute it's convenient that every example we've done we were able to separate the variables as we've said, so it's worked out quite nicely.